Hello, all my chemistry students. I hope this finds you doing well. We are going to start our first podcast for Chapter 12, and you can see the title there. It says Chapter 12, Chemical Bonding. And so we're going to make sense of how all of these elements do come together in the different types of chemical bonds and why all fall we were able to write these wonderful balanced equations and go through stoichiometry. Does that seem like a long time ago? Well, today we're going to talk about types of chemical bonds. And the first thing is a bond that holds groups of two or more atoms together. And this is something that we have been taking a look at all year long. We just haven't really defined it and we haven't really used this in terms of our theory. And it should make sense to you that it takes a certain bond energy to break that chemical bond in those chemical reactions, whether we talked about if it was synthesis or decomposition or single replacement, double replacement. There's all kinds of energy that's going along to break these bonds and form new products. So the first type of bonding that we're going to talk about today is ionic bonding. And I think you'll find that this is a pretty simple little concept to understand. And remember we talked about that all elements want to try to become like a noble gas. Remember, noble gases are very stable. And some will attain this configuration by going through ionic bonding. And what this is, electrons are transferred from a metal to a nonmetal. And you need to remember that it's always the valence electrons that are going to be used in bonding. And so these valence, I'll spell that out for you so you know how to spell that. So these valence electrons are the outer shell electrons. They're the ones that we used in forming or making our Lewis dot structures. So just those electrons on the outside are the ones that are going to be transferred from a metal to a nonmetal. So again, if I label this as a metal and I label this as a nonmetal, you should understand that when they come together, this metal is going to have a positive charge, and that means that it has lost electrons, and this nonmetal is sitting there ready to gobble them up and take them in and find a new home so that you can form this ionic bond. So I have a metal and I have a nonmetal. Recall that when there is this electrons transferred, this positive charge becomes a cation, a charged element, and this negative side is called an anion. And together they are forming what we are calling this ionic bond. Now, they are just sitting side by side by side. Ionic bonds are crystals, and they will have a positive and then a negative and a positive and then a negative, this whole crystalline structure, and they just sit side by side. If you take a really close look at your salt crystal that you have in your salt shaker at home, you'll see that you have a cubic structure. And so these would continue to align in a cubic structure, and for your salt shaker it would be NaCl, and they would continue to align in this cubic faced structure. Okay, so if we talk about how this happens, the cation that I just mentioned, an atom is usually a metal, transfers away one or more electrons. So if we take a look at potassium, potassium needs to get a +1 charge to become a noble gas configuration. So it loses one electron. Or if you take a look at aluminum, you would say, oh, it's aluminum +3. So that means it's lost 3 electrons. Anion formation would be the opposite, where electrons are going to be transferred into an atom. And if we take a look at oxygen, okay, why is my pen not working? If we take a look at oxygen, oh, probably because my hand's on there, sorry about that. If we take a look at oxygen, you can see that it's going to take in 2 electrons. And that's going to receive its noble gas configuration. So we're going to do some drawing of some very simple drawings that'll be very easy for you guys to quickly understand. We know orbital diagrams now, and if we're going to use calcium, we certainly can be using the shortcut methods all along now. We know that argon has a full noble gas configuration that's filled, and then to get to calcium we're going to go to 4s, 2, and then it says to draw one for sulfur. So if I'm going to do the same thing for sulfur, the noble gas configuration that's completely filled for sulfur would be neon, and then we would have a 3s2 molecule, and then we have a 3p, and that would be 3p4. And so remember Hund's rule, they all have to be parallel spin first before they can be paired up. And if we want to take a look at what's actually happening here, so calcium is going to be our metal, So that means it's going to be a cation. It's going to want to transfer both of these electrons so that it can get to argon's configuration. And so it's going to fall, that electron's going to fall right into that, nicely into that p orbital. This one is going to do the same, and now you can see that sulfur has also a completely filled sublevel in the 3p, now to the 6. And so we have calcium that is +2, we have sulfur that is -2, and so they are very balanced. So these are a transfer of electrons. Again, my cation is transferring electrons to my anion. So properties of ionic compounds, I already talked about the crystalline solids, like your salt shaker, the NaCl that you have in your cupboard probably. High melting points, they conduct electricity when melted or dissolved in water. So when they change and they transfer these electrons, we are talking about their sizes, their ionic size. So positive ions, so we are talking about cations again. They are formed by metals. They have low ionization energies. Remember, that means it's very easy to take that electron away. So positive ions are smaller than their neutral atoms when we talk about their size. Well, if I take a look at sodium, you should be able to recognize from the periodic chart its atomic number is 11. So that means I have 11 protons and 11 electrons. So I have my neutral atom. When it loses that one electron and it has lost it to something else that wants it, I still have 11 protons, but now I only have 10 electrons. So remember that size has to do with that Zeph, that effective nuclear charge. Well, this is really balanced. That Z factor is very, very balanced. Well, over here, I have more protons in the inside with more energy there, able to pull those electrons in. So the effective nuclear charge increases here, and the ion becomes smaller. Now it's going to be opposite for the negative ions, which are my anions. If I take a look, they are formed by nonmetals. We know that the electrons are going in. They have high electron affinity. They really want to take in those electrons. But the negative ions are larger than their neutral atoms. So opposite of what we just said about the positive ones. So if we take again, look at chlorine, chlorine's atomic number is 17. So I have 17 protons and I have 17 electrons. And over here, I'm still going to have 17 protons if I have chlorine. That cannot change. But I've added in another electron now. And so that electron's coming in. Why is that arrow pointing that way? I'm not exactly sure. I copied that right from the textbook. I have 18 electrons. So that electron has come into that ion, and you can see that effective nuclear charge is not going to be able to be as strong, and it's going to be a larger in size when it becomes an ion, when it becomes a negative ion. So that effective nuclear charge that we talked about in the last chapter plays a part in this ionic bonding. Okay, so really quick here, we're going to review some things that we did in the last chapter, that if we do an orbital diagram for potassium, you can see again the noble gas is going to be argon, and it is a 4s1 element. Electron dot diagram, I have one electron in the outer shell, so that's K with one dot. It is a metal. It's going to lose that electron, so its symbol and charge is going to be +1. Now on the opposite end, if I take my anion, my nonmetal, which is going to be fluorine here, I have a 1s orbital, and then I have 2s, and I have a 2p5. And so I have fluorine in the 7th halogen family. If I take another color here, I should be able to see that if I take a look, I have this empty orbital right here. Well, fluorine has 7 valence electrons. So if I draw those around, this should make sense. That's 2 dots there. And I have 7 valence electrons. Now, it's going to, when we have the anions, we show where that electron is coming in. Sorry, I did the same thing. So I have 7 valence electrons, and I'm going to show now where this electron is going to come in when it becomes an anion. It comes in the 8th spot right here. You put brackets around the outside, and it has a -1 charge. And so you can see that I have potassium with a +1, fluorine with a -1, and they will be incredibly balanced, and they would form an ionic bond by transferring their electrons. And they're doing this again to reach noble gas configuration. So if I show the same thing again here quickly, I have potassium that has 1 valence electrons. I have sulfur that has 6 valence electrons. Sorry about that, my pen is not cooperating with me. I have 6 valence electrons. There's 6. And my electron dot ions. So I should recognize that potassium is a metal. It's going to transfer 1 electron. Sulfur is a nonmetal, and it has 6 valence electrons. Let's see if I can do this a little bit slower. And there's my 6 valence electrons. So what's going to happen here is sulfur needs 2 electrons to become a noble gas configuration. So here's my spot where those 2 electrons can come in, and I have a -2 charge. Well, this potassium only has 1 electron to give away. Well, how am I going to balance this out? I simply am going to have 2 potassium ions for every sulfur ion that I have. So my chemical formula then here would be K2S. And this goes back to what we did in the fall. You look up on your cation anion sheet, potassium is +1, sulfur is -2. Lowest common factor would be that I need 2 potassiums for every 1 sulfur. You've written this formula many times. And you wrote down the compound name. It would be potassium sulfide. Remember, it has an IDE endings. So hopefully this is coming now full circle with what we have talked about in the fall. In the fall, we would have just simply written this chemical formula, and we didn't really understand why or where all the electrons were coming from. And now we're applying the theory to that. So all those formulas that we wrote when we were crisscrossing the charges, anything that we use in an ionic bond, it became because of the transfer of electrons. I hope all of you have an excellent day, and I can't wait to see you back in class. Talk to you soon.